My name is Givi, and this is Xavier. Okay, so what are microbubbles? Any bubble that is smaller than 10 micrometers, which is 0.00001 meters, is classified as a microbubble. These microbubbles are so small that they can fit inside your bloodstreams and travel in your veins and circulate. But why would anybody want bubbles in their blood? The answer is that they can hold oxygen, DNA, and even drugs, and can be used for medical purposes. So now I'm going to go over the purposes that we use this for. People who have cancer usually have it in a specific area in their body. If you do give them drugs that are harmful to the tissue and cells, you don't want to have these drugs go to all the places in your body and damage your healthy tissues. Therefore, we put these drugs into encapsulated bubbles that travel to a specific location without spilling the drug. And we can use sound waves to direct them to a specific location, as you can see. And once they get there, apply high-intensity sound waves and pop them. And what this allows us to do is deliver this drug in one location so that you don't have to damage healthy tissue and get other side effects from the drug. And the drug dosage is also brought down, and you don't have to take more than you need. Now, what we worked on in the lab were oxygen bubbles. This is another series of bubbles that is filled with pure oxygen. Now, imagine a small child whose lungs failed on him, and he cannot breathe. Usually, these patients, unfortunately, die because of lack of oxygen. Putting a face mask won't do anything because their lungs still don't work. So what we do is we engineer oxygen bubbles and save the lives of these patients. We inject these bubbles directly into the blood, and as you can see in this picture, they're flowing in the blood. And once they enter the blood, the red blood cells, which is drawn right here, there's hemoglobin in the red blood cells, which takes out that oxygen and absorbs it. So therefore, what we have done is given oxygen to people without them having to breathe. Therefore, these patients will be able to survive until their lungs are either regenerated or they're treated by doctors. Okay, now the bubble chemistry, the actual molecular level, we can see that we have the oxygen core, which is pure oxygen inside. The reason why we want to have lipids, which are surrounding the bubbles, is because we want to keep the bubble stable. Without this lipid surrounding this bubble, this oxygen would flow out of the water. So why this works is because lipids have a hydrophilic head, which likes water, and hydrophobic tail, which hates water. And this automatically lines up this way. The tail faces the oxygen, and the head faces the water, and we form a bubble that is able to survive longer than a few seconds. And they can last for days and hopefully weeks and even years. In the lab, we also want to produce these bubbles on a macroscopic scale because if we're going to use this as medical purposes, you don't only want to have one bubble. That's not going to do anything. So how we engineer this is we have a tank where the oxygen flows in and the lipid flows in. Once these two are already in the tank, we apply sound waves using an ultrasound machine, and these mix together to produce bubbles out here. So the magic formula would be lipids plus the oxygen and sound waves produce oxygen bubbles. So our research concentrates on creating stable bubbles, bubbles that last for a long time. We want to manufacture this and sell them. We don't want to have doctors finding half of the bubbles disappearing because they were not stable. We want to determine best storing conditions. How do we put them? What are their properties? Does temperature affect them? Does pressure change them? What is the pH level to store them? And most importantly, we want to test them in vivo, living organisms, and to see how it affects them. We don't want to give bubbles to people if it harms them. We want to see that it doesn't actually react with the blood or messes things up. So now Javier will present some of the data we have collected.
Alright, so one of the problems that we had was that the microbubbles were not lasting for a long time. As Givi said, we need to send the microbubbles over to a hospital all the way to Boston. And it will cause a problem if after we send it, we ship it off, it's going to die off. So that would be a problem. So we perform a stability test. We wanted to know if leaving the microbubbles in the refrigerator will be more stable than leaving it outside in room temperature. Okay. So this is the results that we obtained for the stability test. It is a comparison of gas percent loss, which is the amount of microbubbles over time. You can see it right here. And over time, as you can see, both the non-refrigerator and the refrigerator microbubbles lost gas, but the refrigerator one lost the most amount of gas. So over here, that's the refrigerator one. It was losing gas, but the non-refrigerator one lost the most amount of gas over time. Okay. So we concluded that the microbubbles left in the refrigerator are more stable than the ones left in room temperature. This is another graph that we have. We performed another experiment. We want to know if rotating the microbubbles will prevent the bubbles from merging together. So from this graph over here, we observed that the microbubbles were increasing in size over time. These lines right here represents the micro. What? Okay. So these lines represent the microbubbles increasing every day. Okay. So this is another graph that we have. It's a comparison of the gas loss of the rotating and standing microbubbles. This proves that our hypothesis was wrong. Rotating the microbubble does not prevent them from merging together. So here you can see the standing microbubbles. They were losing gas percent, means that they were losing microbubbles, and the one rotating was losing microbubbles too. So as you can see, the one standing was losing the least amount of microbubbles. This is another graph that we have. So this one is the comparison between the size and the over time. And as you can see, the standing microbubbles were increasing in size. We don't know if they were dying off or they were merging together into with other microbubbles. But we think they were disappearing since small microbubbles have a tendency of disappearing. Okay. So from this experiment, we concluded that that rotating create more kinetic energy, thus creating more stability, since the microbubbles of bumping into each other, thus breaking. And collision with the wall also causes damage. Our future studies is in the future we are planning on creating more lipid solutions, but with different formulas to see which formula is the best one to create stable microbubbles. We also want to test different methods of creating the microbubbles. We are currently using sound waves to create them, and we want to determine the elasticity of bubbles. We want to know how long it stretch, and so these are our references and our acknowledgments. We would like to thank Professor Mark Gordon, our mentor, S. Ross and Nathan Lee, our co-mentors, the Chemical Engineering Department at Columbia for letting us work there, Dr. Sack, and College Student Society. Thank you.